Hey, this is Horner. We're going to look at problems for the photon model and the EM spectrum problems. So here we go. First one says, what is the energy in EV? So initially we'll find it in joules and then we'll just convert it within the problem to EV of a photon of visible light that has a wavelength of 500 nanometers. So remember your equation for the energy of a photon is just equal to Planck's constant times the frequency. Do remember that frequency is equal to the speed of light over the wavelength. So here's what we're going to do. We're going to put h times c over lambda. So that's the same thing. We've just substituted that in. So now we can go ahead and plug all of our numbers in. This is 6.63 times 10 to the negative 34th times the speed of light, which is 3 times 10 to the 8th, divided by the wavelength. And notice that it is 500 nanometers, so that'd be 500 times 10 to the negative 9th meters. And then they want this in EV. So since this will give you joules, we know that 1 EV is equal to 1.6 times 10 to the negative 19th joules. And that should give us our answer in EV. So if you multiply everything on the top, divide by the product of everything on the bottom, you should end up with about 2.5 electron volts. And that would be the energy of that photon of visible light. For number 2, this is a second problem. It says, what is the energy in EV of an X-ray photon that has a wavelength of only 1 nanometer? So same thing we did before. E is equal to hf, where we said f is c over lambda. So this is h times c over lambda. That's going to be equal to 6.63 times 10 to the negative 34th. We're going to multiply that times 3 times 10 to the 8th, and then we have a 1 times 10 to the negative 9th meter wave. So that gives us an energy in joules of 1.99 times 10 to the negative 16th joules. If you go ahead and convert that into EV, you divide by 1.6 times 10 to the negative 19th, you should get about 1200 EV. So a lot more energy in this one than we did have in the previous one. Let's go ahead and switch to the next problem. This one says, oops, let's back up one. Rod cells in the retina of an eye detect light using a photopigment, and that photopigment is called rhodopsin. They want to know what is, if we have 1.8 EV is the lowest photon energy that can trigger a response in rhodopsin. So what they want us to do here is find out what is the maximum wavelength of electromagnetic radiation that can cause this transition. And then the other thing they want us to do is figure out in what part of the spectrum is this. Okay, so here we go. We know that E, from what we said before, is equal to HF, which is equal to hc over lambda. And so now we want to find out what is the wavelength. So we're going to say wavelength then, we can get rid of this, is equal to hc all over E. H, remember, is 6.63 times 10 to the negative 34th. That's times 3 times 10 to the 8th for the speed of light, all divided by 1.8 EV. Now we have to be careful because this is in standard units. This is not. So we need to do go to joules here. So that'd be 1.6 times 10 to the negative 19th joules per EV. So we could have just converted this to joules first and then plugged it into the equation, but we just did 2 steps in one. So this would be about 690 times 10 to the negative 9th meters, which is 690 nanometers. That would be in the visible range, so it would be visible range, and that would be somewhere in the deep red light. So in this part of the spectrum would be visible part of the spectrum nearest the deep red light end that you would have. That's number 3. Let's take a look at number 4. I have a 193 nanometer wavelength UV laser for eye surgery. It emits about 0.5 millijoules at a time in a pulse. They want to know how many photons does this light pulse contain. So what we'll do here is we're going to just say the number of photons should be equal to the total energy divided by the energy per photon. So that should be equal to the total energy divided by hc over lambda, and that will give us the energy per photon. So this is equal to 0.5 millijoules, 0.5 times 10 to the negative third joules. We're going to divide that by our h, which is 6.63 times 10 to the negative 34th. We have 3 times 10 to the 8th meters per second. Then we're going to divide that again by 193 times 10 to the negative 9th meters. If you do that math, you should end up with 4.85 times 10 to the 23rd photons. That's a huge number, and that's kind of what we would expect from this. Next problem is number 51. And in number 51, now we're switching to looking at temperatures again. It says the spectrum of a glowing filament has a peak at a wavelength of 1200 nanometers. They want to know what is the temperature of the filament, and here they want it in degrees Celsius. So we'll do it in degree Kelvin first. I'm sorry, in kelvins, not degree Kelvin, but just in Kelvin, then we'll switch it to degrees Celsius. So remember we said that the peak wavelength in nanometers is equal to 2.9 times 10 to the 6 nanometers times Kelvin all over the temperature. So they gave us 1200 for our nanometers, so now we can say T is equal to 2.9 times 10 to the 6th, all divided by that 1200 nanometers. Remember, this is in nanometers already, so you don't have to convert this one, and we end up with 2417 K. In order to get to degrees Celsius, all we do here is we take that 2417 K and we subtract off 273 degrees, and that will give us 2144 degrees Celsius. So Kelvin here is just your degrees Celsius plus 273. So Celsius is going to be Kelvin minus 273, and that's where that comes from. All right, let's go ahead and take a look at the next problem. For the next problem, this is number 6. Our sun has a surface temperature about 5800 Kelvin, and that gives us a peak wavelength in the middle of the visible spectrum. So let's say we go to a different star, and we want to find out if it has a 400 nanometer average wavelength. We want to know, which is in ultraviolet, we want to know what is the temperature then for that star. So temperature again is equal to 2.9 times 10 to the 6th nanometers times a Kelvin all over that peak wavelength. We go ahead and put in our number here, 2.9 times 10 to the 6th, and we're going to divide that by 400 nanometers. Remember, this is in nanometer Kelvin, so I don't have to switch this one, and that does give me 7,300 Kelvin. That's the minimum temperature. So any hotter star would also peak in the ultraviolet as well. There are a lot of stars like that. Other cooler ones, cooler than the sun, are even more numerous. So there's a lot of these, but just not as many as what we have with the temperature of our sun or less. The next one is our last problem. This one is the photon energies used in different medical X-ray imaging. They do vary widely depending on the application. A single dental X-ray uses photons about 25 keV. The photon energy for microtomography, this is a process that allows repeated images in a single plane at varying depths within a sample, is 2.5 times greater. So what are the wavelengths used in the X-rays and for these three purposes? Okay, so for the very first one, what we're going to do here is, for these two purposes, sorry. I said three. First one, we need to say the frequency is equal to the energy divided by Planck's constant. So this is for the first purpose. We said that that one's 25 keV, so that's 25,000 eV, all over 6.63 times 10 to the negative 34th. That's in joules times a second. So we need to convert this to EV. So that'd be 1.6 times 10 to the negative 19th joules for every 1 EV. That way the joules cross off and we're left with a frequency, which is something over a second. So this is 6 times 10 to the 18th hertz. We also need to find the wavelength then. Remember, wavelength is just C over frequency. So this is 3 times 10 to the 8th, all divided by the frequency, which is 6 times 10 to the 18th is what we just got. And so we get 5 times 10 to the negative 11th meters. But remember, we usually do these, let's do this one a picometer. So this would be 50 picometers. So 50 picometers, really small. Letter B, this would be for something 2.5 times greater. So I'm going to take 2.5 and multiply it times 25, and I end up with 62.5 keV. So let's go ahead and find this. F is equal to E over H. Our energy here is 62,500 because it's kilo EV. And we divide that by H, 6.63 times 10 negative 34th. Our problem is this is an EV and this is in joules seconds. So we need to say 1.6 times 10 to the negative 19th joules all over 1 EV. And that gives us 1.5 times 10 to the 19th hertz. We're going to convert this like we did last time into wavelength. So that'd be C over F. So this is 3 times 10 to the 8th divided by 1.5 times 10 to the 19th. That's a pretty high frequency. So this is 2.0 times 10 to the negative 11th meters, which is 20 picometers. So extremely small. And that is the end of the problems for this section.